Let's wait for a couple of minutes, then I will start. Okay, let me start. This is the 11th week, the problem solving session for the course Introduction to Atmospheric and Space Science. So here we will be doing those assignment questions, of course, for the week 11, and some assignment numerical questions. I have already taken it. So there will be 3 numerical questions which appeared in the week 11 assignment, and after that some concepts which will be helpful in solving the numericals as well as conceptual questions which are present in week 12. That will be helpful, like the gradient drift, then curvature drift, what are those concepts, And then planetary ring currents, I will write some expressions. Then magnetic mirroring, which is an important concept in order to solve certain questions. And after that, a brief introduction about the air glow and aurora I will put, because some questions are also there from that, and some numerical questions which will be helpful in solving the assignment questions in uh, the week 12. Okay, therefore let us start with the assignment questions and see what are the questions. This is the assignment 11, that is corresponding to the week 11. Okay, the first question in the assignment 1 is, when a particle with charge q and mass m is placed in a uniform static electric field. Very important, the uniform static electric field, you have a charge q, you have a charge, if you have a mass m, and it is placed in a uniform static electric field, then what will be the uh, these options are given. For example, particles velocity linearly increases with respect to time, then total energy is conserved in this motion, work done by electric field is zero in this motion, and the fourth option is all of the above. So let's see once again. Also, I have already done this in the previous session. Okay, so this is the first question of the assignment, where it has been said that you have a uniform and static electric field. Let's draw then, this is x, y and z, let's say, and let us consider whatever the situation which we have considered in the previous problem solving session, that is the Ez, or the electric field, is in the z direction only, right? And there is a charge with mass m which is moving in this uniform static electric field, and we have written the expressions for Vx equal to maybe 0 and Vy is 0. Yeah, they are 0, not maybe 0, but they are 0, and the z direction velocity is the only component of the velocity which we have got in a uniform static electric field, which is equal to the Vz0 plus q by m Ez into t, which is a linear relationship with time. What about Vx and Vy? They are nearly constant. So Vx0 and Vy becomes Vy0, because the dVx dt is 0, dVy dt is also 0. So this is the initial velocity which has come, and this is the z direction velocity. Therefore, we can see that particles motion is linearly related to the time. So linearly related to time. Therefore, if you see the first option, that is particles velocities linearly increases with respect to time, is true. The second option is the total energy is conserved in this motion. So let's see whether total energy is conserved in this motion, which we remember that yes, the total energy is conserved and the work done, the net change in work done is 0. So this we have already seen, but still if we have to solve this question properly, then what we have to do? See, the force is nothing but q into E. Therefore, m dv dt is actually q into E. And also, this is a conservative force, so del cross E is actually 0. Therefore, E can be written as minus gradient of phi, some potential. Okay. Now, if I just dot it with velocity, then what it will happen? So, v dot dv dt, and it will be nothing but q E dot v. And this can be written as d dt of half mv square, which we can easily see. This is half mv square, and this is q into E is minus grad phi dot V. And I will just write this particular expression. Let us take the minus outside, and this will be delta phi by delta x I cap, the gradient definition, delta phi by delta y j cap, and delta phi by delta z k cap, and you dot it with delta x delta t I cap plus delta y delta t j cap plus delta z delta t k cap. Ultimately what we are getting is minus q d phi dt, because phi is now a function of time only. Therefore we are getting d dt of half mv square, the kinetic energy, and q into phi, the potential kind of energy, is 0. Therefore half mv square plus q phi is constant. This is the energy conservation. This is the energy conservation. Okay, so this is the energy conservation, and if the energy is conserved, then the change in work done will be equal to 0. Okay, therefore in the first question, this entire case of the uniform static electric field, when a particle with a charge q and mass m is placed in the uniform static electric field, which I have derived in the earlier class, earlier problem solving session. From there, whatever the conclusion which we have derived, those conclusions are nothing but the options here. Therefore all of the above should be the correct option corresponding to question number 1. Coming to the second question, it states which of the following statements is true. Number 1, magnetic field exerts force only on a moving charge, which is true, which is true. So if I just go to the second question, now this magnetic force Fb, no electric field is present, suppose, so Q into V cross B, this is the force. Now if V is 0, then of course this Fb should be equal to 0. That is very intuitive. Therefore the first option is definitely correct. That is, magnetic field exerts force only on a moving charge. Second thing, electric field exerts force on a stationary charge. Well, yes, electric field exerts force only on a stationary charge. See, you have to remember about this thing only. It, no doubt, the electric field definitely applies on a stationary charge, but we have seen in the first question also, we have seen, but also in a moving charge, which we have seen just now. We have seen the uniform static electric field. We have just seen that both are applicable. Therefore the second option, that is electric field force exerts force on a stationary charge, only on a stationary charge, that is wrong. Magnetic field exerts force on charge moving parallel to the direction of the field. No, we have seen that magnetic field, if the magnetic field is in the z direction, Bz, and if the q is also moving in this direction, then V cross B is 0. Therefore that is not possible. Therefore A option should be the only correct option. Okay. Going to the third question. A particle having mass m and charge q is at rest. On applying a uniform electric field on it, it starts moving. What is the kinetic energy when it travels a distance x in the direction of the force? It's simple, it's very easy. This is the third question. So what is there? It's just that a q is present, stationary, and electric field is in this direction. Therefore the net force will be what? Q into E, which is well known to us. Now, because of this force, it has already displaced a distance x. Then what will be the work done? That is equal to Q into E into x, or the kinetic energy is nothing but QEX. This is simple. Okay. Fourth question is, if a particle of mass m and charge q enters in a homogeneous magnetic field with velocity this, simple, Vx, Vi and Vz, then trajectory of the particle in a homogeneous magnetic field will be, we all know, that is helical. How it is helical? Because in the x and y direction it forms a circle, and in the z direction it moves linearly with time. So z, in the z direction it moves linearly with time, but in x and y, circular motion. So the resultant is a helical movement. Right? So B is the correct option, helical. After this, we have a fifth question, sixth question and seventh question are the numericals, which I have already put. So I am not going to do it now. Just after this assignment, other questions are finished, I will start with that. Now the term E by B has the dimension of, see, E is the electric field, B is the magnetic field. We have known to this particular thing that 5, 6, 7, this is the 8th question. This V drift or charge separation velocity is actually E by B. Therefore, it definitely has a unit of meter per second or velocity. Right? This is a simple thing. Or else you have to do using the basic force of magnetic field, what is the unit of that, and then electric field, what is the unit of that, and then you have to come to the conclusion that it is a velocity. But if you know that the velocity drift, which we have earlier also derived, that V is equal to E by B or E cross B by B square, then we can easily clearly see that E by B is nothing but the unit of the velocity. The ninth question is, the drift velocity of the charged particle in a uniform electric and magnetic field depends on, again, drift velocity. So it does not depends on the charge on the particle, then mass of the particle and the velocity of the particle. It only depends on the electric field and the magnetic field. So the expression actually comes to like this. So V drift is either you write it E by B or you write it E cross B by B square. So no charge velocity. No, of course this it is not dependent on velocity, because it's the velocity's expression which we are finding out. So it will be not depending on velocity as well. And the third option was what? Mass of the particle. So it is not also dependent on the mass. Okay, and the last question is, this I have already shown. If the RL is the radius of gyration of a particle in an inhomogeneous field, then the scale of inhomogeneity L should be. So for inhomogeneous field, the radius of gyration RL is much less than L. That is the scale of inhomogeneity. Okay. So these are all the assignment questions which we have seen and solved, and the remaining numerical based questions which we will going to do just now. Okay, just a minute. Okay. So this question is, the radius of the gyration for an electron of kinetic energy given to be 10 mega electron volt in the Earth's magnetic field of this will be. Therefore, we need to find out. So, what are things given which we'll first write? So, given is the kinetic energy of the particle. Kinetic energy of electron. There is some network issue. Okay, the kinetic energy of the electron, which is given to be about 10 mega electron volt. Okay, and the magnetic field B is 0.45 A to 10 to the power minus 4 Tesla. This is also given. Now we need to find out. The radius of gyration. So already the magnetic field is there. Now kinetic energy, which means that the electron is moving with a particular, so electron is here, it is moving with a particular velocity v, and the magnetic field is somewhere here. So ultimately what will happen is that it will have some helical path whose radius is nothing but the radius of gyration r, or RL you can say, doesn't matter. So RL will be equal to mv by qb. Just a minute. Yeah. So now it's mv by qb. But do we have the velocity? No. We have the kinetic energy, but we don't have the velocity. So we convert this RL's expression, this radius of gyration's expression, in terms of kinetic energy. How we will do it? Simple. We know that kinetic energy is nothing but half mv square. Therefore, what we will do is that 2k by m and its root is nothing but velocity. Just substitute this expression here. Therefore, Rn will be equal to m root over 2k by m divided by q into b. Therefore, we get root over 2m into k divided by q into b. This is the final expression in terms of kinetic energy and the radius. We know that the mass of the electron is 9.11 into 10 to the power minus 31 kgs. We know that the q of the electron is 1.6 into 10 to the power minus 19 coulombs. B is already given, kinetic energy is already known. Therefore, now we can calculate this particular expression for the radius of gyration. Therefore, RL will be equal to root over the kinetic energy, which is 10 into 1.6 into 10 to the power minus 13. Remember, because it is in electron volt, mega electron volt, so 10 to the power minus 13. If had it been in only electron volt, then it is 10 to the power minus 19 divided by 1.6 into 10 to the power minus 19 into the magnetic field, 145 into 10 to the power minus 4. Now we have to calculate how much it will come. Let's see. So this is minus 31 and this is 13 already there, right? So 10 to the power minus 44, and that gives 10 to the power minus 22 here because root is there already, and this is 10 to the power minus 23, right? If I calculate the above expression, let's see how much it comes. So it's 2 into 9.11 into 10 into 1.6. Okay. So it's about 291.52 divided by same 1.6 into 0.45. So this root will be there. If it would be root of 291.52 is 17.07 divided by 1.6 divided by 0.45. It comes out to be about 23.71 into 10. Therefore, it will be 237.1 meters. This is the answer. Let us see whether this is the answer or not. This is the question number 5. Yes, 237 meters is the correct option. Okay, let's go for the question number 6, the next numerical. So this is the essentially is very easy question which is there in the assignment, and where only the radius of gyration has to be calculated, where you know we have done this kind of question earlier also as a practice, so that we can easily solve this question in this assignment if it is present. And I think it is very easy if you have already seen and practiced all those questions which we have done in the previous solving session. The next question is the ratio of the radius of gyration of alpha particle and an electron of same velocity in a magnetic field of 0.01 Tesla will be. Mass of the alpha particle is given, and we know that the mass of the electron is known to be. The most important fact here is that we need to find out that, again, we have to go to this radius of gyration. Number two is that it has same velocity, it has the same magnetic field. It has not given that there is a same magnetic field, but ultimately in the same magnetic field it is moving, both the alpha particle and the electron. Therefore, just write the expression of the radius of gyration. So writing the expression of radius of gyration, what is that? RL, again, so this is RL, is mv by qb. Now write it for the alpha particle. So RL alpha will be equal to m alpha, v alpha, q alpha and b alpha. See, this b alpha and v are the same thing, and r of e is nothing but me v divided by qe and b. So v and b are same. So since v and b are same, therefore if I have to calculate at all, calculate the ratio, so RL of alpha divided by RL of electron, then what we will be left behind? So it's m alpha divided by q alpha, me divided by qe. So it's just the mass to charge ratio and its corresponding ratios. Okay, and now just this is the ratio which we need to calculate. We know what all the things we know. M alpha is given, we know the QE, we know ME, we know Q of alpha. How much is Q of alpha? Is 2 times the Q of electron. How much is M of alpha? It's actually 4 times the mass of the proton, but we have to just put the expressions now. Therefore, RL of alpha divided by RL of electron is nothing but 6.64 into 10 to the power minus 27 kgs, which is the mass of the alpha particle, divided by 2 into the charge of electron, 1.6 into 10 to the power minus 19. Even if you don't write, just write QE, the QE will cancel. So this will be 1.6 into 10 to the power minus 19, the charge of electron, and at last the mass of the electron, which is this. Right? So this and this I cut out. Therefore, now if I do this, it comes out to be about 0.3644 into 10 to the power 4, this power which is left. So this will be 3644 and it should be the answer. This is the amount of, or this is the ratio that the radius of gyration of alpha particle will be with respect to electron. So what does it mean? So this alpha particle will move like this with a greater radius of gyration, where this becomes RL of alpha. But on the other hand, if you see the electrons progression, it is like this with a smaller circle. Okay, and where this is RL. So it's about 3644 times. Let's see the answer. It's 3648 given, so it's 3644 is fine. And the last is this easiest question. If the cyclotron angular frequency omega of an electron is 10 to the power 9 radians per second, then the value of the magnetic field will be. So it's a cyclotron frequency based questions. So just we will write the expression of the cyclotron frequency and just calculate it, just put into the formula and you will get the result. Okay, so this, the expression of cyclotron angular frequency is omega given by q into b by m. This is the expression of the cyclotron frequency, which we have seen earlier class. Okay, now it is given that this omega, let us write it given. So it is given that omega is 10 to the power 9 radians per second. Then the value of the magnetic field will be, is the question, and the particle is known to be electron. Therefore, what is its mass? We already know this. It is 10 to the power minus 31 kg. Okay. Now, just put the expression and find out the electric field, sorry, the magnetic field. So, B will be m into omega by q. What is m? 9.11 into 10 to the power minus 31. What is the omega? That is 10 to the power 9 divided by 1.6 into 10 to the power minus 19. So now just do it. What we get is about, so this 10 to the power minus 31 and this 19, if it comes plus 9, so it is about 10 to the power 28, so it would be 10 to the power minus 3, and this is 9.11 divided by 1.6. Let us calculate and see how much. It's about 5.69. So 5.69 into 10 to the power minus 3 Tesla. This should be the answer. Very simple and easy question based on the formula, and we have already seen in the previous problem solving session that this is the cyclotron frequency. We have already also seen what is the time period, and let's just check once last. Yeah, it's 5.68 into 10 to the power minus 3 Tesla. So all the questions of these assignments we have seen already. The 11th week assignments questions are clear now. Now we will move towards some week 12 concepts which will be helpful, like the gradient drift, then curvature drift is there, then planetary ring currents are there, then magnetic mirroring, through which whether the particle which is in the magnetic field, whether it will reflect or be trapped or be lost. This kind of what is the condition behind this particular behavior of these particles, this we have to understand. Some briefings about this air glow and aurora has to be known, because certain questions are there which will be helpful in understanding those questions. These concepts will be helpful. And at last, certain questions, numerical questions which I have randomly framed, will be helpful in solving certain assignment questions which are there in week 12, and understanding certain of these completely concepts. Okay, so I will start with the gradient drift theory. Just a minute. Okay. I will start with the gradient drift and move towards the curvature drift slowly. Okay. So this is the gradient drift. What is the concept behind gradient drift? So let us write first. What happens is that often the magnetic field in a plasma varies with position, time. But earlier in case where we in the 11th week we were solving about uniform magnetic field and static magnetic field. So these cases are completely different now. This is a kind of an inhomogeneous because it is varying with position. So it's an inhomogeneous magnetic field and not a static magnetic field right now, because it may also vary with time. Okay, so whenever in the plasma the particles or the magnetic field is varying in position as well as in time, causing the plasma particles to drift. Okay, and the second thing which happens is that the perpendicular kinetic energy, is changed. Okay, this is the second point which we get. And since this magnetic field varies with space, with positions of space, this is no longer homogeneous. So this magnetic field becomes inhomogeneous. Now, if the magnetic field becomes inhomogeneous, then we have to define an scale L, which is the length of inhomogeneity. That is a length or an upper limit up to which the magnetic field is homogeneous, above which it is inhomogeneous. Therefore, this another condition which we have already seen in this, there is a question in the week 11 assignment that RL should be much less than L. But what is this RL? Is radius of gyroscope. Right? This is an important criteria in the inhomogeneous magnetic field. Okay. Now, let us consider a case where, you have three axes. Let us make. So this is your Z, suppose. This is your Y. Oh, sorry. This is X. This is Y. Then only X cross Y will be Z in this direction. Okay. Now, in such a way, the magnetic field is oriented that this field's direction is in the Z. Okay, the B magnetic field is in this direction, but the magnetic field is varying only in Y direction. Therefore, magnetic field is in Z direction. Gradient of magnetic field is only in Y direction. This is our assumption. We have taken it as per our own simplification or simplicity. Okay. Just a minute. Fine. So this is the case. Now, if I have to write magnetic field at some radius equal to some xc, suppose any value which is I am denoting will be equal to b at r is equal to 0, that is at the center, plus where we need to find out the value, that is xc, because 0 is the reference center, dot grad of b, and this grad of b is actually nothing but delta b by delta y, because this grad b is only in the y direction. the way we have defined. Okay, and this x in terms of the radius of gyration will be RL sine omega t, or or y will be equal to RL cos omega t, right? Such that the position vector will become a circle RL square, which we have seen, because otherwise the radius of gyration will not take place. Therefore, this Vx therefore will be equal to V perpendicular cos omega t. Just sign will be cos, because if you are differentiating, Vy will be V perpendicular sine omega t, right? Therefore, Fx will be equal to Q Vy Bz, because the magnetic field is only in the z direction. Okay, so further if we write, so it will be Q V perpendicular sine omega t into B naught plus minus RL cos omega t into delta B delta y, right? Now if I average it, this Fx, one period averaging, if we do, then it is nothing but, see, this is sine omega t cos omega t. Now if this average can be written as this half sine 2 omega t, and this comes out to be 0. The mean average of this particular thing is 0. But if you go to y direction, we have minus q vx bz, because now the terms will be staying, because b is only in the z direction, right? So we can write minus q v perpendicular cos omega t b naught, again plus minus RL, right, cos omega t, delta b by delta y again, right? But now we have cos square omega t as in the average, and this is minus q v perpendicular, whatever you have, okay, and then RL is there. So this cos square omega t, its average, of course this delta b delta y is also there, so this comes out to be minus q v perpendicular RL delta b by delta y and divided by 2. This value is half, okay, so this becomes my Fy average, and Fz average is 0, because nothing will be there in that. Okay, so we are getting this, a force which we are getting like this. Okay, now the velocity Vf due to this gradient of the magnetic field, which is oriented in the y direction, can be written as 1 by q f cross b by b square. Now from where we are getting this expression? We are getting from drift velocity. Remember, it is E cross B by B square. So E can be written as F by Q. That is what we are writing. And it is only having the Y component. So Vf will be equal to 1 by Q. And you have minus Q V perpendicular RL delta B by delta Y. Now this is in the J cap cross Bz, which is in the K cap, divided by B square or Bz square, whatever you write. Now J cross K will be minus I, right? So J cross K will be minus I. So therefore minus, it will be V perpendicular RL divided by 2 Bz delta B delta Y into I cap. Now this RL will have, So RL will have mv by qb. You can put it there also. Just a minute, I have to put another screen between. Yeah, okay. So we can further write this v grad b, the gradient of b is written as minus b. So it is m v perpendicular square by 2 is already present. This is q, bz square you can write, and this will be delta b by delta y. This should be the expression, right? Yeah. And you can see that this is nothing but the kinetic energy, the perpendicular kinetic energy. So it's minus the kinetic energy by q bz square delta b delta y, and it is in I cap direction. Therefore, what will happen? So this is the concept behind this. So you have z, you have x, you have y. B is in this direction. So this is the bz. Okay, and you have grad b in this direction. So where you are getting, so if it is ions, q is greater than 0, positive, so the ions will move in the negative x direction, like this, with a larger circle. These are for the ions, but for electrons, q is negative and makes it a positive. This is for the electrons going in the positive direction. So it will move in positive x direction. If we take the gradient of b in the y direction and b is only in the z direction, then this will be the, so it will move, ions will move in negative x direction. Simple. Okay. So one thing to notice is that this j cross k, so if you just write to understand what will be the sign convention, see j cross k is I, therefore this j cross k should be positive I cap, and there is a negative sign already present. So this negative sign is actually creating this negative and positive opposite kind of a theory. Okay, so this is the gradient drift. Due to this gradient of the magnetic field, is giving a drift. Whose velocity is given by v grad b is minus kinetic energy divided by q bz square into delta b by delta y. This is the expression in the I cap, right? Okay. The immediate next thing is the curvature drift. We have now seen, already we have seen the gradient drift, that is, if there is a gradient in the magnetic field, what will be the expression of the drift velocity. But now if there is a curvature, means magnetic fields is moving or the particle is gyrating in a magnetic field which is curved, then at that point of time there is also a drift which the plasma experiences or the plasma particle experiences. Again, all these are valid only when we consider the amount of plasma is less or the plasma particle theory. Okay, so we will just quickly write down what is this curvature effect means and derive just one line expression, which is very easy expression. So, and write the total gradient drift as well as the curvature drift together to form the drift velocities. Okay. So first is the curvature drift. Okay. So let us write what is this curvature drift means. So curvature of magnetic field lines can also cause plasma particles to drift, right? Now as the particles move along the curved magnetic field, which I will show how it will move. It experiences a centrifugal force. Of course, if there is a curvature, then radially outward from the center, there is a centered outward directing force, which is the centrifugal force, which is due to the field curvature. And therefore drifts where perpendicularly outward. Drifts perpendicular. Let's write like this: perpendicular to both B and centrifugal force. Very interesting. So what is happening? So suppose this is the magnetic field line which is curved, and a particle is gyrating in that particular field, and this is the RC, the radius of curvature. Okay, this is the magnetic field which is curved. Okay, and this is the centrifugal force Fc, and this is the V parallel, right? Now this F curvature is actually nothing but mv parallel square by Rc. You can write it Rc vector by Rc magnitude, which is Rc square, right? We can write this as a vectorial form. Now V curvature, drift velocity curvature, can be written as this force F v parallel square by Rc square by Q. The same way, the force per unit charge, that is the electric field, cross, that is not cross, that is Rc cross B divided by B square. Simple. So this is the, again, the drift velocity. So how is it coming? The same E cross B by B square. Okay. Therefore, the total drift, so the total drift, all possible, is nothing but V due to the gradient drift and V due to curvature drift. So it finally can be written as, let me write the expression of the final the drift velocity. So let us write the vectorial expression for the drift velocity, which is nothing but 1 by Q, right, m V parallel square divided by RC square B square, right? This is RC cross B plus MV perpendicular square divided by Q into 2 B cube. It is B cross grad B. Now you just change the expression of grad B to delta B delta Y, and B to BZ K cap, and this is J cap, and this B will be automatically cancelled out. So this is the final expression of the total drift. So we have seen that drifts are possible in case of a plasma, if we consider plasma as a particle in an inhomogeneous magnetic field. Now in that inhomogeneous magnetic field, what is the meaning of that? Which is varying in position and time. Now in this kind of magnetic field, there is a possibility that the plasma particles will be get a drift. Now what is this drift? Where is the concept coming from? It is coming from the drift velocity, that is E cross B by B square. Simple. So this E electric field can be written as force per unit charge, and simple we have just assumed that in case of a gradient drift, there is a gradient of magnetic field which exists, which is creating the inhomogeneity, and B is present in the Z direction only. On doing that and averaging what will be the force, we have only seen that Fx is 0, Fz is 0, Fy is only present, and using that Fy we have found out the expression of the drift velocity, and final expressions comes out to be like this, which shows that in the I cap direction the movement or the gyration will take place. And then the curvature drift, we have seen that when the magnetic field is curved, suppose, which is the radius of curvature, in that particular way the magnetic field is oriented, then the centrifugal force will act, and that divided by the Q becomes the electric field corresponding to that, and then just write the expression of the curvature drift. So this ends the concept of the drift velocity in the plasma particles. One is the gradient drift, another is the curvature drift. Now in the immediate next thing is the planetary ring currents. I will just write the current density of the gradient as well as the curvature currents which are present. So just write the expressions to understand, and after that I will go with the magnetic mirroring and then solve some 4-5 numericals which are there in the last couple of minutes, and we can wrap up. So as I have mentioned that these planetary ring currents, I will just mention, so here I will mention the current density expression. Just like we have the gradient drift and curvature drift, we also have a curvature driven current density and gradient driven current density. Therefore this J of grad is actually given by N QE into V of grad. This is the drift velocity for the ions minus V of grad of the electrons. Okay. Now what is this N representing? It is nothing but the number of ions, that is number of the electrons. For plasma we generally consider to be the same. And what are these? This is nothing but the gradient drift velocity. Gradient drift velocity for ions, and the same for electrons, right? And QE is known to us. It's the charge of the electrons. And the second thing is the JR, which is corresponding to the curvature effect. Okay. So this expression becomes NQ V or R of ions and VR of electrons. Same expression. Okay. Now J gradient. Sorry. So this J gradient can be further written as N by B cube. Just writing the this V grad of ions and V grad of electrons. Just changing that and some changing the in between parameters. This is W perpendicular of ions minus W, this is plus W perpendicular of electrons, and you have B cross grad B, the same expression which we have for the gradient speed. Now these are nothing but the kinetic energy, right? These are the kinetic energies, and for simple JR it will be 2n by RC square B square. Similar expression which we have seen already now, but this is for the parallel component of the kinetic energy, and this will be RC cross B. So these are the important expression for the current density. So it is current density due to gradient and this is the current density due to curvature drift. Okay, so these are the two expressions for the planetary ring currents which I have written. Okay, the next concept is the important concept, which is the magnetic mirroring. It will take some time to understand what is the magnetic mirroring thing. And means mirroring means that some kind of reflection will take place or the particle will be lost. So when it will be reflecting, what is the condition for the reflection to occur? This is what we are going to derive here. So the condition for the plasma or the magnetic field where we will get the particles to be reflecting, that is there is a reflection kind of the particles will take place, or the particles will be trapped, and if it does not satisfy that particular criteria, then particle will be lost. Simple. This is the main clearing concept. Now I will start just a minute. Okay. So I will start with the expression of the magnetic moment. So this magnetic moment is, as we know, that it is defined as that the current cross the area. This is the area. And mu is how the magnetic moment is represented. It is mv perpendicular square divided by 2b. Okay. And also we know that the radius of gyration is RL is equal to mv divided by qb. Right. Now, what we will do here is that we have a magnetic field like this, somewhere weak, somewhere very strong. So where the magnetic field lines are placed very close, they are the stronger areas, and where the magnetic field lines are separated very large distance, that is the weaker section of the magnetic field. So this is the strong region and this is the weak region. Weak B, strong B. And the B, direction of B is in this direction. Direction of grad B is also in this direction. Okay, so direction of B and grad B are same. Suppose this is the Z. Okay, so we will use cylindrical coordinate frame system. So how it will look? It will look like this. So suppose this is the thing. This is your cylinder, and in this cylinder, this is your R. Okay, this is your phi, and this is the Z. Right. So here B will be equal to BZ. What is B phi? 0, because B is only in this Z direction. Okay. Now what is BR, which we will see. Okay, because magnetic field is there in the R direction. Right? Okay. Means it's changing in the R direction. Okay. So now what I will do is that let's write the magnetic field as a vector as BR R cap, B phi phi cap, and BZ Z cap. But B phi is 0, which we have assumed, and BR R cap as BZ Z cap. Why? Because B phi is 0. Okay. Now this grad of B can be written as 1 by R. So this is not the grad of B. We know from Maxwell's equations we know that del dot B is actually equal to 0. No divergence of that. Okay. So how to write in the spherical, not in the cylindrical coordinate, the divergence delta delta R of BR into R, okay, plus 1 by R delta B phi by delta phi plus delta BZ by delta Z should be equal to 0. But this is also 0. Therefore, we get 1 by R delta delta R of RBR plus delta BZ by delta Z should be equal to 0. Correct? Now 1 by R delta delta R, again writing the same, BR will be equal to minus delta BZ by delta Z. So RBR, now we are already started integrating, 0 to R I will write. So it will be R delta BZ by delta Z into delta R, right? Therefore RBR will be equal to minus R square by 2 delta BZ by delta Z. So 1 R and this R will be cancelled. So BR will be equal to minus R by 2 delta BZ by delta Z. This is the relation between BR and BZ. Just a minute. Okay. Now, this is the expression which we are getting, and we will use this expression. But before that, we need to understand what will be the force, and it will be only the magnetic force, no electric field. So since no electric field, F will be therefore Q into V cross B. And what is this F? Is M dV/dt. Is nothing but Q into V cross B, isn't it? So now Fr will be what? Q B V phi Bz minus Vz B phi F phi Q into minus Vr Bz plus Vz Br and Fz Vr B phi minus V phi Pr. Right? Now let us only consider this Z component. For time being, let us take the Z component. So taking only Z component now. Okay, so Fz will be what? See, B phi is already 0. Therefore, it will be Q with a minus V phi Br. And what is Br? We have just now got, it's minus Q V phi, which is there, and R delta Bz by delta Z by 2, I think. Right? Okay. So now what we will do is that, okay, so this will be dvz by dt will be equal to minus q v phi by 2m r delta bz by delta z. Okay. Right. Now, okay, remember that we have put the mod br over here, this region. Okay. That's why this negative sign will be there. Okay. Now, dvz dt is nothing but minus q by 2 v phi is nothing but v perpendicular, because the magnetic field is in this direction and phi direction is like this. Okay, so this will be v perpendicular by m rl and delta bz by delta z. Clear? Now I will take out this m on this side and multiply by vz, so that I can reach to kinetic energy. So it will be minus q by 2 v perpendicular vz rl delta bz by delta z, isn't it? Now further, if we have to do, it's minus q by 2 v perpendicular vz. Now this will be m v perpendicular by qb delta bz by delta z. So I can chop out these q's, and further we can write as minus m v perpendicular square divided by 2bz. Right? delta Bz by delta Z, and this Vz can be written as delta Z by delta T. Okay, so what we finally get is, see, this m by 2 V perpendicular square is there, which is representing nothing but the W perpendicular, that is the perpendicular kinetic energy, divided by Bz, which is there already, and delta Bz by delta T. What is this? This is nothing but half m Vz square, which is nothing but V parallel square, okay, and d dt is there. Why this? Because Vz is nothing but V parallel, because it is in the direction of the magnetic field. Fine. Just a minute. Okay, so finally then what is the expression which we are getting in terms of kinetic energies? So d dt of this is W per sorry, not perpendicular, this is parallel, because it is in the direction of the magnetic field, and that should be equal to minus W perpendicular by Bz dBz by dt. So this is an expression which relates W parallel and W perpendicular. Clear? Now d dt, energy conservation, is half m V parallel square plus half m V perpendicular square. That should be equal to 0. So half m V perpendicular square is actually mu into B. This is the expression which this is magnetic moment. This is actually from the expression of the magnetic moment that we are getting into this. Okay, the first expression which we have written, see this one. So this is the kinetic energy perpendicular, so that is mu B. Okay, yeah, this is what we are getting. Now just put it in the expression. So d dt of half m V parallel square plus mu B should be equal to 0. Now this half m V parallel square is nothing but W parallel. Just write this expression and try to find out. So see, this is also depending on this mu thing. See, this is also mu, right? Because W perpendicular by B. So this is also mu. Therefore, we can write it as minus mu dB dt plus d dt of mu B. So mu dB dt plus B d mu dt, and that is equal to 0. You chop out these two. So what you are getting? Mu is constant. So the magnetic moment is conserved in this process. Okay. Now what is happening? Now the next thing, that is the criteria. So suppose this mu is mv perpendicular square divided by 2b, and what is this v perpendicular? Is actually v sine theta. Okay, so this mu becomes mv square sine square theta divided by 2b, and that is nothing but the kinetic energy times sine square theta divided by b. Okay, now this theta So this theta is actually an angle between the actual velocity vector, and this is the v parallel. So this is your theta, and this should be definitely the v perpendicular. Therefore, we are getting an expression that is mu by ke is actually sine square theta by b. Very important expression which relates the theta, which is an angle between the velocity vector and the parallel direction, that is the direction of the magnetic field, and with relating with the kinetic energy, it relates with magnetic field as well. And another expression which I have to write, for that I need another page. Yes. Another thing which is important is that suppose you have the maximum magnetic field Bm, and you have the initial magnetic field, say B naught, okay, and this magnetic field is moving in this direction, the z direction, then this sine square theta m divided by Bm will be equal to sine square theta 0 divided by B0. Okay, because this kinetic energy in the earlier expression, this kinetic energy is also conserved, mu is also constant, so this is a constant. So if there is a change in the magnetic field from initial weak value of the magnetic field to some final strong value of the magnetic field, this is the maximum value, then this expression is also true, right? And we another defined a term, so it's mirror ratio. So this mirror ratio is Bm by B0, so the maximum by the zeroth. And finally also, so this is sine square theta 0 will be equal to B0 by Bm when for the trapped case. Now, how to know the trapped case? So theta m will be equal to 90. So whenever this theta which we have defined is greater than or equal to 90 degree, reflection or trapping takes place. But when theta is less than 90 degree, particle is lost. Also there is a theta c, which is the critical angle, sine inverse of root of B0 by Bm. So if sine square theta 0, if it is greater than equal to B0 by Bm, then again reflection. If it is less than B0 by Bm, particle is lost. So conditions are like this. Okay, so this is the magnetic mirroring concepts which are there, and I will give some brief introduction about the aurora and air glow that will help to solve certain questions, and after that we will do some 4-5 numericals, which is easy numericals, and end up today's class. Okay, so I will write certain points which will be helpful to understand. Okay, number one is that air glow is a global phenomena which is seen. So air glow is global and is seen at every point of the earth. Okay, and if I change the color for the aurora. So aurora is local and is seen near the polar regions. Okay. The second point is air glow is due to the interaction of solar radiation with atmospheric constituents. What about aurora? Change the color. So aurora, what is that? So aurora is due to some charged plasma particles to interaction of highly energetic solar wind particles, which are nothing but the plasma particles, with constituents of atmosphere in the presence of magnetic field. Right. The third thing is air glow intensities are very low, of the order of 100 Rayleigh. Of the order of some 100 Rayleigh. Rayleigh is a unit which tells us about how much photons are there per second per centimeter square. So it's kind of an intensity. Okay, and just check what will be the value of this Rayleigh, which is easily available in the internet. I am not writing it right now. This may be one of the question. And auroral intensity are very high. You might have seen this auroras, which occurs in the polar regions particularly during Antarctica, is aurora australis, and you have in the North Pole as aurora borealis. So these are very high intensity thing. So in some kilo Rayleigh. Okay. And the fourth thing is about the what you call as luminosity. So the luminosity of air glow is uniform. Whereas if you come to aurora, its luminosity is mostly structured, and if you see the sources of this aurora formation or this your what you call as the air glow formation, the constituents are oxygen and nitrogen mostly. oxygen and nitrogen mostly. And so which of this constituent is helpful in giving this particular, what you call as the colors? That is, for that I just write two expressions, and these are the energy states. Just draw it. Write it first. So this is 2 0 1 0. So this is 3p. This is 1d. So this d state, s state, p state, like that. Okay, and you have, if electron jumps from this state to this state, so this photons is released. Again, if it jumps from here to here, another photon release. This is of h nu. Okay. Now this is actually the 630 nanometer, and this one is about 557 nanometer. So I will write the reaction. So this is oxygen 1s gives oxygen 1d. So these are the states. From 1s to 1d, if it jumps, then it releases a photon of 557 nanometer, which is the green line. So it is green line day glow emission. Okay, and another is the O, which is 1d to O 3p plus h nu, which is about 630 nanometer, and this is nothing but the red color. So this is how this red color and green colors comes. So this auroral as well as air glow, these things will help you to solve certain questions. There are many questions which are there based on this. So whatever I have written here, it is easy for, if you just read this also, it is easy to do the questions of the next assignment. And at last I will do some numerical problems which will help to do the 12th week assignment questions. So it will be easy for you to do it. Okay. Okay, so the question says, calculate the drift velocity at this particular point if the magnetic field varies as B is equal to A by Y. So Y is the variable, and the magnetic field is varying not in Y direction but as A by Y, and where A is given to us, and the kinetic energy of the proton in the magnetic field is given to be 2 electron volt. Okay. So here, as we can see, this B is equal to A by Y, and this drift velocity which has to be found out is nothing but the gradient drift. Sorry. So because no curvature terms are given, if curvature terms has to be given, then radius of curvature should be given. Therefore, we can deduce from the question that we need to find out the V gradient of B, and which is nothing but mv perpendicular square divided by 2q B square and delta B by delta Y in the direction of Y, suppose. Okay, the gradient is there. Now, what all things are there we need to find out. See, this mv perpendicular square by 2 is nothing but the kinetic energy, and kinetic energy we have here. Okay, So kinetic energy divided by the charge b square. P is also given, I think. No, we have to calculate. We have to calculate using this. And delta b by delta y. Okay. So first let us find out b is equal to, see, a by y. So what is delta b delta y? It is minus a by y square. Okay. And we have to calculate where? At y is equal to 3 into 10 to the power 6. So we know the value of a. So 2 into 10 to the power 4 divided by, now this y square is 3 into 10 to the power 6 whole square. Right? So it will be nothing but minus 2 into 10 to the power 4 divided by 9 into 10 to the power 12. And that gives you about 2 by 9 into 10 to the power minus 8. You can keep a minus sign, or don't keep a minus sign, it does not matter. So there is a minus sign which is present here also. So it's just tells you the direction, but we need the drift velocity magnitude first. Okay. Now this kinetic energy is given. Therefore, let's start calculating. Oh, okay. Now B is nothing but 2 into 10 to the power 4 divided by 3 into 10 to the power 6. So it will be 2 by 3, 10 to the power minus 2. Okay. So the B square we need. So it will be 4 by 9 into 10 to the power minus 4. Right. So the V gradient of B will be equal to, so minus m for a proton is known 1.6. Oh, it's not required because kinetic energy is already given. So 2 into 1.6 into 10 to the power minus 19 into the delta b delta y, that is minus minus you cancel, 2 by 9 into 10 to the power minus 8 divided by, you have the charge which is about 1.6 into 10 to the power minus 19 and the what you call as the b square. So it is 4 by 9 into 10 to the power minus 4. So this 1.6, this gone. So what you have is about, so it's 2 by 9, 2 into 2, 4 by 9. So it's completely gone. So now what is left behind is about 10 to the power minus 4 meter per second. Exact similar type of a question is there in the assignment. So you try based on this similar kind of formulation, only you have to proceed. So this is just a rough question which I have prepared, and you have to go ahead along this line only and you have to come to the answer. The second is the kinetic energy of the proton in the direction of the magnetic field is 3 electron volt. Now the curvature radius is this, which is perpendicular to B is equal to 1 Tesla. Find the curvature drift. So now the curvature drift needs to be found out, given that the kinetic energy is 3 electron volt. Next what? RC, the radius of curvature, is also given, 4 into 10 to the power 6 meters. The B, the magnetic field, is given to be 1 Tesla. And the V curvature we need to find out. What is the expression of that? So it's mv parallel square divided by q. RC B sine of 90, because it is perpendicular, it is given. So it's RC square B square. Okay. So this RCB can be chopped out. Just you multiply by 2, you divide it by 2. So it becomes, this becomes your W parallel square, and this is the kinetic energy. The parallel kinetic energy is given here. So it will be 3 into, or 2 is there also, 3 into 1.6 into 10 to the power minus 19 divided by 1.6 into 10 to the power minus 19 into 4 into 10 to the power 6 B is also 1. Therefore this and this gone, so it's 6 by 4, so it's 3 by 2 into 10 to the power minus 6. So it's 1.5 into 10 to the power minus 6 meter per second. Okay. So this is corresponding to the curvature drift. Although these values is I have just randomly put, it may not be the actual values. That's why maybe we are getting this very small amount of this curvature drift velocity, but the concept remains to be the same, the formula remains to be the same. Okay, another question is to find out the angle between the velocity and the magnetic field. That is in the magnetic mirroring case, which we have seen that there is a velocity and this is the V parallel, which is the direction of the magnetic field, and this is the angle theta. Then for different kinetic energies and given magnetic field and magnetic moment, can we calculate what is the theta? So in the first case, you have given that kinetic energy is 2.5 electron volt, and the second case it is 2.5 mega electron volt. So how much change it take place, that is what to see. So 8 into 10 to the power minus 19 is in joules per Tesla, which is the magnetic moment, and B is 0.5 Tesla. And we know very well know from the expression of magnetic mirroring that is sine theta will be equal to root over mu B upon kinetic energy. So you just have to calculate. So 8 into 10 to the power 19, sorry, minus 19 into your 0.5 Tesla divided by 2 into 2.5, I think, yeah, 2.5 into 1.6 into 10 to the power minus 19. Okay, so now if you calculate it out, it comes out to be about 1. Therefore theta should be equal to 90 degree. On the other hand, in the B case, the kinetic energy is 2.5 mega electron volt, nothing but this extra 10 to the power 6 will come. So 8 into 10 to the power minus 19 into 0.5 divided by 2.5 into 1.6 into 10 to the power minus 30. So it will come out to be nearly 10 to the power minus 3 after taking the root. So theta will be very small. So just this amount of change, 10 to the power 6 change in kinetic energy, will give you the theta to be also very small. It's very close to the parallel direction that the velocity vector will move. Okay, and the next question is calculate the magnetic moment. So we have to calculate the moment here with the same formulation only we will calculate. So the magnetic moment needs to be calculated if the pitch angle is of the Larmor's device is about 30 degree. So you can write it, mu is equal to just sine square theta, again coming from that magnetic mirroring thing. This is the B. So mu we need to calculate, so this will be sine square 30 into kinetic energy is about 3 electron volt divided by the magnetic field, that is 0.8 Tesla. So it will be 1 by 4 into 3 into 1.6 into 10 to the power minus 19 divided by 0.8. So this is 2 and this 2 will cancel out. So it will be 1.5 into 10 to the power minus 19 joules per Tesla. Simple formula based questions are there. And the last question is corresponding to that Larmor's radius, which is nothing but the radius of gyration only. So mv upon qb. And we have already seen that in terms of kinetic energy can be written as like this. We have already seen too many times. And the kinetic energy is known to us, that is 12 electron volt, and magnetic field is about 0.4 Tesla. Even if the angles are also given, still it does not matter, because the radius, the kinetic energy when it is given, you don't need to take the component of that, because it's a scalar. So it's just you put the values and get the result. So this is what is the thing which is given. And one more thing is required here, that is the mass. So mass, we have seen for alpha particle, it is 6.64 into 10 to the power minus 27 kgs. So that much mass we can write and find out the expression. So it will be RL will be equal to root over 2 into 6.64 into 10 to the power minus 27 into the kinetic energy is 12 into 1.6 into 10 to the power minus 19 divided by, you have Q, that is 1.6 into 10 to the power minus 19 into 0.4 Tesla. You just calculate it out. See, this is minus 27 and 19, so it will be about 10 to the power minus 46, which we can take out from the root as 10 to the power minus 23, and there is 10 to the power minus 19 which is left in the denominator. And if I just calculate the other things in the numerator, so it becomes 2 into 6.64 into 12 into 1.6. Take its root, we get 15.96 divided by 1.6 into 0.4. So divided by 1.6 divided by 0.4, it comes out to be about 24.94 into 10 to the power minus 4. So about 0.2494 into 10 to the power minus 2 meters. So that gives you 0.249 centimeter. So this should be the answer. But what we have missed here is that this Q is nothing but 2 into Q, because this is the alpha particle. So the charge is actually 2 into Q. Therefore, it will be divided by 2. So it will be about 0.125 centimeter. So this is the Larmor's radius, and this ends today's class. So what we have done is that some numerical questions which I tried to fix so that we can easily do the assignment questions, and I have given some glimpse about the air glow and aurora, which will be helpful to solve certain questions. And these magnetic mirroring concepts, whichever important formulations are there, I have derived those. And planetary ring currents also, some curvature related and gradient related current densities are just the expressions I have put. And we have in detail seen the curvature drift as well as the gradient drift derivation. And these are the 11th week assignment questions which we have solved. And so this ends today's lecture. Next week we will solve the 12th week assignment and some more questions if we can see from the previous years, then we can discuss those questions. Oh, thank you. So you have any questions, or you are prepared for the exam? Great, brilliant, brilliant. So come on that day, on the 12th week, the next week, then we will solve the 12th week assignment questions, and with some previous questions also we will repeat, so that it will be a revision for everyone. So that will be helpful, and the question will be easy, I think. So in the exam also, whichever I have given, they are generally very simple and easy. If you go through those notes which are present in that NPTEL lecture notes, just read those and solve certain assignment questions and numericals which we solve in the these problem solving sessions. It will be very helpful for you. So you will be easily doing it. So it will be done very easily. Okay. So let me. Okay, thank you. Goodbye. Stop share this.